A glance back at the growth of physics. The year 2025 marks a significant milestone in the history of physics. It has been exactly 100 years since it was unequivocally established that the laws governing the microscopic world are fundamentally different from those that govern the macroscopic world we see around us, and that these laws can only be understood through the language of mathematics. In simple terms, it's been a century since we began to comprehend the principles of quantum mechanics, the branch of science that describes the microscopic world. In this context, it feels fitting to look back at the key phases in the development of physics. Physics, at its core, is the study of the physical universe. Naturally, this field has two main branches, one focused on the matter found on Earth and the other on the celestial bodies like stars and planets. While the motion of stars and planets is generally governed by gravity, our understanding of the materials that make up both the heavens and Earth relies heavily on the theories of quantum mechanics. Although significant progress has also been made in the gravitational theory over the last century, this presentation focuses on a brief overview of the development in the realm of quantum mechanics. The concept that matter is composed of tiny indivisible particles, atoms, was first suggested by Democritus in the 5th century BC. However, a clear understanding of the atomic structure only emerged much later in the 21st century, nearly 2500 years afterward. While scientists like Pascal, Hooke and Newton made extensive contributions in the 17th century concerning the general behavior of matter, detailed studies about the atom were still lacking during that time. Most of the scientific focus then was on the general properties of matter, its states like solid, liquid and gas, and the characteristics like density and elasticity. In the early 18th century, contributions from the scientists like Bernoulli and later the inventions of the steam engine alongside the Industrial Revolution played a key role in the development of thermal physics. Progress in electricity and magnetism, along with the wave theory of light during the 19th century, greatly influenced the direction of physics. Key discoveries such as Thomas Young's demonstration of the wave nature of light in 1801 and John Dalton's atomic theory in 1803 deserve special mention. The 20th century witnessed unprecedented advancements across all areas of physics. The contributions of great scientists like Ampere, Faraday, Maxwell, Hertz, Kirchhoff, and Boltzmann are truly invaluable. By the end of 20th century, except for a few phenomena like atomic spectra, blackbody radiation, and photoelectric effect, most aspects of physics could still be explained using Newtonian mechanics or wave theory. The observations made by Lord Kelvin in the late 19th century is very famous. There is nothing to be discovered in physics now. All that remains is more and more precise measurements. However, what happened was something else. In 1897, J.J. Thomson discovered the electron. In December 1900, to explain the blackbody radiation, which had remained unexplained until then, Max Planck proposed that energy in electromagnetic radiation has a particle-like nature. Although Planck's explanation wasn't taken seriously at first, in 1905, Albert Einstein accurately explained the photoelectric effect, which had also remained unexplained, using the particle nature of radiation. Later, In 1930, using the Planck's constant, Niels Bohr explained the Bohr atomic model and atomic spectrum. As a result, the Planck's constant came to be accepted as a universal constant essential for explaining the microscopic world. Subsequently, up until around 1925, a new mathematical framework was being developed to explain the microscopic world. By around 1925, a new branch of physics called quantum mechanics took shape. In 2025, it completes 100 years since the beginning of its development. During this period, the realization emerged that the laws governing the microscopic world are fundamentally different from those in macroscopic world, and the human reasoning alone is insufficient to understand them. It was also understood that studying subatomic particles requires new equations and hypotheses, and the mathematics is the only way to comprehend them. Just as Galileo in the early 19th century revolutionized the existing scientific approach by asserting that true science must be revealed through experiments and observations, the emergence of quantum mechanics marked a shift from the traditional observational methods. With quantum mechanics, a new awareness emerged that even if the concepts revealed through the mathematics are entirely different from the external macroscopic world, they must be accepted if they are experimentally verified. Mathematics became the tool to explain the microscopic world and to formulate new ideas. As quantum mechanics completes 100 years since its inception, a brief summary of some major discoveries and observations made during the past 100 years is given below. Although we have come to a long way in our journey to understand the fundamental principles of the universe, there are still many cosmic truths that remain unexplained. The ongoing research on neutrinos and experiments using the Large Hadron Collider are expected to help us gain a deeper understanding of the mysteries of the universe in the near future.